Imagine traveling to stars light years away, not in thousands of years but much faster. This is the dream of faster-than-light or FTL travel. It is a journey beyond our current reach, a vast cosmic ocean we long to explore. Scientists and dreamers have pondered this for generations, looking for ways to cross the immense distances of space. It's a challenge that pushes the boundaries of our knowledge. We look up at the night sky, filled with countless stars, and wonder how we might ever visit them. This grand ambition fuels our curiosity and our scientific endeavors, pushing us to think in new and exciting ways about the universe. For a long time, we have known about a cosmic speed limit. The great Albert Einstein taught us that nothing with mass can travel at the speed of light. Light itself, made of massless photons, zips through space at an incredible 300,000 kilometers per second. To push anything with even a tiny bit of mass to that speed would require an infinite amount of energy. This fundamental rule of physics seems to put a firm stop to our interstellar dreams. But what if there are new ways to understand how the universe works, especially in very extreme conditions? Perhaps there are equations and ideas we haven't fully explored yet. This is where new ideas like the N.E.W.T equation come into play. N.E.W.T stands for Neutron-Electron-Weighted Total. It is a fresh concept, a mathematical tool designed to help us think about how things might behave beyond the speed of light. Its main purpose is to try and calculate how certain patterns, or what scientists call frequency-relevant manifestations, might show themselves if they were to somehow exceed this cosmic speed limit. It is not about building a spaceship today, but about understanding the fundamental possibilities that might exist within the laws of physics, or perhaps even hint at new laws we are yet to discover. The N.E.W.T equation invites us to consider the universe from a different angle. It suggests that by looking at the tiniest particles and how they interact under immense forces, we might find clues. It is a journey into the theoretical, a way to explore what-if scenarios. Think of it as a special map for uncharted territory in physics. This equation aims to help us understand how matter itself might behave in conditions so extreme they are hard to replicate, like near a black hole or during the universe's earliest moments. It's about peeking behind the curtain of the known universe. Everything you see around you, from the stars in the sky to the device you are using now, is made of incredibly tiny building blocks. These are called subatomic particles. The main ones we often talk about are protons, neutrons, and electrons. Protons have a positive electrical charge and, along with neutrons which have no charge, they huddle together in the center of an atom, called the nucleus. Electrons, which have a negative charge, are much lighter and they zip around the nucleus in a kind of cloud. These particles are the fundamental Legos of the cosmos, assembling in countless ways to form all matter. Usually these particles interact in predictable ways. Protons and electrons attract each other because of their opposite charges, which helps hold atoms together. Atoms then join to form molecules, and molecules make up everything else. These interactions are governed by fundamental forces, like electromagnetism, which is responsible for light and electricity, and the strong nuclear force which keeps the nucleus of an atom from flying apart. These are the forces that shape our everyday world, the gentle rules that allow stars to shine and planets to form, creating the universe as we know it and experience it daily. But what happens when these tiny particles encounter truly forces? Imagine the crushing gravity near a black hole, a place where gravity is so strong that not even light can escape. Or think about the immense electromagnetic fields that might exist near exotic objects like neutron stars. Under such powerful influences, could these subatomic particles start to behave in ways we have never seen before? Could their properties change, or could they interact in new and unexpected manners? Scientists believe that understanding these extreme interactions is key to unlocking deeper secrets about the universe's fabric and its fundamental laws. The N.E.W.T equation is specifically designed to explore these very questions. It focuses on how protons, neutrons, and electrons might respond when subjected to forces so intense that they could, theoretically, push effects beyond the speed of light. It considers their individual properties like their mass and charge to calculate a total weight. This weight is then used to predict how their collective behavior, their orientations or patterns, might manifest in these extraordinary high-energy environments. It's like trying to understand how a tiny boat, a particle, might behave not just in a calm pond but in the middle of a cosmic superstorm. So, how does the N.E.W.T equation actually attempt to peer into this realm beyond light speed? Its core purpose, as we've touched upon, is to calculate something called orientations of frequency-relevant manifestations. Let's try to simplify that. Imagine everything in the universe, even tiny particles, has a kind of rhythm or a buzz. This is related to its frequency. A manifestation is just how something shows itself, its pattern or behavior. The N.E.W.T equation tries to figure out the direction or shape, orientation these patterns might take if they could express themselves faster than light. The process, according to the theory behind N.E.W.T, involves a few steps. First, scientists would identify all the relevant subatomic particles, the protons, neutrons, and electrons, within a specific region of space they want to study. Then, they would carefully account for the individual masses and electrical charges of each of these particles. This information is crucial because it determines how each particle contributes to the overall picture. By combining these properties, the equation calculates a total weight for that collection of particles. This isn't weight in the everyday sense, but more like a measure of their combined influence under extreme conditions. Once this total weight is determined, the N.E.W.T equation uses it to predict the orientation of these frequency-based patterns, even if those patterns are propagating faster than light. This is the truly mind-bending part. It's not necessarily saying a solid object will instantly appear light years away. Instead, it might be about how information or an energetic influence or some fundamental aspect of these particles could create an effect that seems to outpace light. It's like trying to predict the ripple patterns in a pond, but if those ripples could somehow spread faster than the disturbance that made them. This connects to a broader idea that some scientists explore, that the universe is fundamentally about vibration, energy, and frequency. While the N.E.W.T equation is a specific mathematical tool, it taps into this concept that everything has its own unique hum or energetic signature. The equation attempts to mathematically describe how these fundamental hums of particles might change and align themselves when subjected to forces powerful enough to challenge our understanding of space and time. It's a way of looking for new patterns in the cosmic symphony, especially in the most energetic and unusual sections of the orchestra. What could understanding such complex particle behaviors through the N.E.W.T equation mean for our dreams of interstellar travel? While it doesn't directly give us blueprints for a warp drive, it could provide fundamental insights. If we can understand how matter and energy might behave or transmit influences faster than light, even theoretically, it opens new avenues for thought. Perhaps there are ways to manipulate spacetime that we haven't conceived of yet, ways that depend on these exotic particle interactions. The N.E.W.T equation could be one small step towards understanding the very fabric of reality needed to even consider such grand voyages to distant stars. Beyond star travel, the N.E.W.T equation could also shed light on some of the universe's most mysterious objects. Think about black holes with their immense gravity or neutron stars, which are incredibly dense remnants of massive stars. These are natural laboratories for extreme physics. The conditions within and around these objects are precisely where the N.E.W.T equation aims to describe particle behavior. By applying such theoretical tools, we might gain a better understanding of what happens deep inside a black hole's event horizon, or how matter is structured within a neutron star, pushing our knowledge of astrophysics into new frontiers. It is important to remember that the N.E.W.T equation is a theoretical concept, a new proposal in the vast field of physics. Science often progresses through such bold ideas which are then tested, debated, and refined over time. Many science fiction stories like Star Trek with its warp drive or Star Wars with hyperspace have long imagined FTL travel. These stories inspire us, and sometimes real science finds ways to explore the possibilities that fiction first dreamed up. The N.E.W.T equation is part of this ongoing dialogue between imagination and rigorous scientific inquiry, a tool for asking profound what-if questions about the cosmos. Ultimately, the N.E.W.T equation represents the enduring human quest for knowledge. It reminds us that there is still so much to learn about the universe. Even if faster-than-light travel remains a distant dream, the pursuit of understanding the fundamental laws of nature, especially under extreme conditions, will undoubtedly lead to new discoveries. Each new equation, each new theory, is a step forward on our journey to comprehend the cosmos. The universe is vast and full of wonders, and tools like the N.E.W.T equation encourage us to keep looking, keep questioning, and keep dreaming of what might be possible.